Here in this video, we are talking about coefficient of thermal conductivity. So before going into that parallel combination, let me quickly tell you what is coefficient of thermal conductivity is. Thermal conduction is a phenomena of transmission of the heat via a solid material where no particle of the medium has a permanent displacement. Each particle is tightly attached to the neighboring molecules, being a solid. Each molecule vibrates about its main position, pass the energy to the next particle, and comes back to the original position. This kind of a transmission is called thermal conduction. The amount of the heat that flows in a thermal conduction via solid material is equal to coefficient of thermal conductivity, directly proportional to area of cross section, and difference between the temperatures. If you call this temperature as theta 1 minus theta 2, that is delta T, that is equal to theta 1 minus theta 2, and is inversely proportional to the length of that conductor. So this can be rewritten as delta theta by L by Ka. That L by Ka is called a thermal resistance. We can write with the letter R, where R is called thermal resistance. That is equal to L by Ka. Once after grasping this basic points, let us talk about what do you mean by thermal conductors in parallel, and then we'll find out the effective thermal resistance and effective coefficient of thermal conductivity when they are connected in parallel, right? So what happens in parallel combination? Let us try to understand what do you mean by a parallel combination. What do you mean by parallel connection? Let us try to identify. This is rod 1. This is another rod. So this is one rod and this is another rod. If their first ends are connected together and their last ends are also connected together, that kind of a connection is called as a parallel connection. Now what happens is, when you supply some heat dq by dt, rate of flow of heat, some part of the heat will go through the first material and some other part will go through the second material. So what we can say is, the total flow of heat, rate of heat of the parallel combination is rate of heat flow that happened through the first rod plus rate of heat flow that happened to the second rod. That's a combination of these two. One thing I want you to understand carefully is, here temperature at one end of the rod is theta 1. The other end also will have a same theta 1 because both of them are starting due to the getting heated up due to the same heat. Here also the temperatures are same. So what's the important thing I want you to get is, in parallel combination, delta theta is same, whereas dq by dt is not same, but that is rate of heat flow is shared. We know the formula for the dq by dt as delta theta by r. So as we know, dq by dt of parallel combination is dq by dt of the first case and dq by dt of the second case. In the place of that dq by dt, I can write delta theta by r. So delta theta by r of the parallel combination is equal to delta theta by r of the first case, basing on this, plus delta theta by r of the second case. But as I told you, delta theta is same, so that can be cancelled. So 1 by r parallel equal to 1 by r1 plus 1 by r2. That's how we can find out the effective thermal resistance when they are connected in parallel. This is similar to that of the electric resistance itself. But we know R equal to L by Ka. This is 1 by R parallel, therefore K parallel A parallel by L parallel. In reverse I have written. because it's 1 by K1 A1 by L1 and K2 A2 by L2. That's the general equation for the effective rate of flow. But I can of course further simplify that further by putting some conditions. If I consider two materials are having same areas, A parallel means heat flows through this as well as through this. That becomes A1 plus A2, that is 2A. And if another condition is given for you that L1 equal to L2 equal to L parallel is not going to become 2L. See, this is 1L. This is one more L. Parallel length is also equal to L because they are not connected in series. In series, lengths add up, areas remains same, whereas in parallel, areas adds up and lengths remains same. Putting these two conditions in the above equation, we will get K parallel. A parallel is 2A. That is when we consider rods of same area of cross section and same length. L parallel is L itself. K1, A1 is A by L. K2, A by L. So L's can be cancelled, areas can be cancelled. 2 into K parallel equal to K1 plus K2. So K parallel equal to K1 plus K2 by 2. That's the one more answer that we want to get. We want to get two answers. Effective resistance in parallel and effective thermal conductivity, and we have derived both of them in this equation. While you are deriving this, I want you to understand the most important part, that what we have to grab here, what we have to get here is this, that in parallel combination delta theta is same, dq by dt is shared. That's the most important part that you need to understand. That's it. Thank you for watching. But I want you to understand carefully that this is valid only when two rods have same area and length. Otherwise, this is not valid. You have to go back to the core equation and solve further whatever the given problem is. That's it. Thank you for watching.